For your test two review, we don't have too many problems to do because we're just covered a few sections dealing with rationals and radical expressions. So let's start up here at this one on number 1 on page 1 of the review. It's in your guided notes book. And let's see if we can split this out and find the perfect squares inside or under the radical. If we can resolve them. First of all, you know that 64 is a perfect square. The square root of 64 is 8. So I can bring that one out from under the radical, and it would be an 8. Any exponent that is even is a perfect square. And how do you resolve those? Well, you find the square root of an exponent, an 8th exponent, by dividing it by 2. So I can say the square root of a to the 8th is a to the 4th. I just took 8 and divided by 2. I do the same thing for b to the 10th. The square root of b to the 10th is b to the 5th. Now that only works for exponents. For numbers, we have to find the perfect square, if it is a perfect square, or we have to find the perfect squares within it. When I finish with this, I don't have anything left under the radical, so the square root sign is gone. All I have is 8, a to the 4th, b to the 5th. Number 2 is a little bit different because it has a negative inside it. So but also because we're looking at cube roots instead of square roots. Now we can find a cube root of a negative number. A negative times a negative times a negative is going to give you a negative. So that works for us. We know that we're going to look for the cube root of 27, and we want the negative of that. You know, we have a positive cube, and a negative cube would give us negative 27. So when I look at 27 and I check my cubes, I realize that 3 times 3 times 3 is 27. So the cube root of negative 27 would be negative 3 times negative 3 times negative 3. Now do the same thing I did with the exponents before. I simply divide them by the index over here. So I'm going to say x to the 9th divided by 3 is going to give me x cubed. And 18 can be divided by 3 too. So I would have y to the 18th is going to be divided by 3 is going to give me y to the 6th. So my answer is going to be a negative 3 x cubed y to the power of 6. Number 3 is, of course, a fraction, and it has a radical under it. And if we can resolve that radical, if we can simplify underneath, it's probably a good idea to do that. You could also split it up into the square root of 9 over the square root of 81 and resolve those. But I know that 9 divided by 81 gives me the square root of 1 over 9. I can already get the square root of 81, right? Sorry, that would be taking out from under the radical. Hang on just a second. I'm not trying to do that first. I'm just trying to divide them. 81 divided by 9 is 9, is what I'm trying to tell you. Okay, so I've got now the square root of 1 over the square root of 9. Now, this just happened to work really well. The square root of 1, of course, is 1. The square root of 9 is 3, and it resolved to 1 over 3. If you had split it into 2 separate radicals, which is what I was thinking about before, I would have had the square root of 9 over the square root of 81. The square root of 9 being 3, and the square root of 81 would be 9, and then you would reduce 3 over 9 to 1/3. So you could do it either way. It should get the same answer both ways. Now let's look at number 4 here. Really, all that we are raising to this fractional exponent is the x, not the 3, okay? You'd have to be in parentheses to raise that 3. So I'm going to write it like that. I'm going to say this is 3 times, and I know it's a square root because it has a 2 as that bottom denominator. So it would be x to the power of 1. Remember how we said it could be inside or outside your radical sign. The exponent could. So all I've got now is 3 times the square root of x, and there's nothing I can do with that. So that's the way we would write it in rational notation. All right, let's try this one. When we have the same base, and these are both x's, raised to an exponent, and they're being multiplied, we can do the multiplication by adding the exponents. Well, this would be basically saying x to the 1/4 plus 5/4. So once I've got that, I said, okay, I can add those because they have the same denominator. This is really x to the power of 6 over 4. Now, they wanted me to write it as another notation in the rational notation. So what I'm going to do is say x to the power of and it's really a fourth root, isn't it? X to the power 6. X to the power 6, and I'm looking at the fourth root. Now, I can still simplify this again because x to the power of 6 does have a fourth root inside it. In other words, 6 is bigger than 4. So what is this can be simplified into, and I'm kind of going to work backwards here. I'm going to say, really, this is the same as the fourth root of x to the fourth times x squared. And now you can see the perfect fourth root, can't you? What's the fourth root of x to the fourth? We're going backwards here again. We're going to say that's x. I took it out from under the radical. I took the fourth root. I said 4 divided by 4 to get it because it's an exponent, and I can do that. And then I've got times what's left under the radical. Well, it's a fourth root radical, x squared. And there's nothing I can do about that because the exponent under the radical is not as big as my index over here, and it has to be at least that size for me to simplify anything. Now this one, everything inside these parentheses is being raised to the 1/2. In other words, let's write it with its symbol, and we're going to say 16 x to the 10th raised to the power of 1. All of that would be raised to the power of 1, which is the numerator up here, and it's a square root, which I don't have to write. Now, can I get any simpler than this? Well, it's a square root. Do you see any square roots inside 16, or is 16 a perfect square? Well, 16 is a perfect square. 4 times 4 gives me 16. X to the 10th is an even number. If I divide that 10 by 2, I get x to the power of 5. So I got everything out from under the radical. What do I have left? Its simplified form is 4x to the power of 5. Let's take a look at number 7 now. This is division. And if I divide, I'm really subtracting exponents. But there's another way when we're doing it with fractional exponents. There's another way to look at it. Let's get everything up into the numerator. In other words, I'm going to subtract this one to take it up to the numerator, right? So this is going to be the same as x to the power of 1/3 times x to the power of negative 1/6. Now, usually we're trying to get rid of these negative exponents, but these are negative fractional exponents. So let's see if we can't combine them first. They don't have the same denominator. But this one, the common denominator, has got to be 6. I can quickly get this one to become 6. I will multiply the numerator and denominator by 2. That would give me x to the power of 2/6. And I still have times x to the power of negative 1/6. Now remember, if you multiply the same base with exponents, you add the exponents. Well, this is the same as saying x to the power of 2/6 minus 1/6. Same denominator. What do I have? X to the power of 1/6. Now, I still haven't written it with its radical notation, have I? I haven't changed it into a radical. So I want to do that. I'm going to change it, and it's going to say x. And it's what root is it? Well, it's the 6th root, isn't it? So it's the 6th root of x to the power of 1. Remember how that works. Now, number 8 is not too bad. I mean, we can simplify this before or after we split these up, and I'm going to split it up first this time. I'm going to split it into 2 different radicals, and maybe that's a good way for me to do this. I'm going to say 5x to the power 4. Square root of that, and the square root of 4, x squared. Now, I'm going to look for perfect squares inside these separate radicals, because that makes more sense to me right now. And you could do it either way, like we did the other one the other way. So it doesn't matter which way you start. There's no perfect square inside 5, but x to the 4th, if I simplify that, it becomes, take it out from under the radical, it becomes x squared. So let's fix that one. It's really x squared times the square root of 5. Let's do the denominator. Well, I know I can take 4 out, and it becomes a 2. I can take x squared, the square root of x squared, it becomes an x. So all I have here is 2x. Can I simplify this again? Can I reduce these fractions? We already know that the square root of 5, we're stuck with it. There's nothing smaller. But everything up here is multiplied. X squared is multiplied times that. 2 is multiplied times x. So we can reduce any of these that are alike. And x squared over x reduces. We would say this is x to the power of 1. We're going to subtract them. And we're going to put the x, leave the remainder. We say 2 minus 1. We leave the remainder exponent wherever we had the larger exponent. So what do we have? X to the power, x times the square root of 5 over 2. Now 9. The best way to do this one is to look for perfect squares inside 50. And you remember me telling you that 50 multiples of money are really easy. Think quarters, okay? If you have multiples of quarters, you know, because a 25 you know is a perfect square. So let's split this one up. And for this, I'm going to write it kind of like this so that hopefully you can see it better. I'm going to say this is the same as 25 times 2. I'm going to leave it all under one big radical. I could split it up into separate ones, but this works. And then I'm going to say, what's the biggest square root that I can get out of x to the power of 7? Well, it has to be an even number. And the biggest even number within 7 is 6, smaller than 7. So I say that's times x, right? So have I got it all? This is 50. This is x to the 7th. It's all still under the radical. Now let's find our squares. This one is, if I pull it out, it becomes a 5. And this one is, if I pull it out, it becomes x to the power of 3. So let's do that. X to the power, x times 5 times x cubed. And what's left under the radical is 2x.